first unit of the semester, but we ended up a little bit behind. That's okay. We are going to do something called stoichiometry. And stoichiometry is dimensional analysis. Dimensional analysis is where you take a unit, you cancel it top to bottom, and you're going to be able to, where we just went from like moles to grams or grams to particles or something like that on the last unit, you're going to be able to be given, hey, there's these two reactants, you have 3 grams of each one. How much product are you going to make throughout this chemical reaction? So this unit is kind of the culmination of many different things that we did first semester. You're going to take your nomenclature, you're going to take your molar masses, you're going to take your predicting products, your balancing reactions, your mole conversions, sig figs. I think I said dimensional analysis already. If not, I'm going to say it again. And you're going to put it all together in these stoichiometry problems. This test is much like the last test where you're going to have just 10 problems and you're going to solve for them. The last test was probably one of the easiest ones that you're going to do all semester. Typically that is not even a full test that was actually stripped out of the last unit that we did last semester. So if you are struggling with finding a molar mass, with how to do dimensional analysis, how to predict products, go to my YouTube channel, Dr. Gable Chemistry, and it's all broken up by unit, and go back and watch some of these videos or ask me questions or something like that, because if you're lost now, you're going to still be lost later on down the road. That all being said, your stoichiometry is the type of math that we're going to do that is based off of your mole conversions. Sorry, I just lost my picture. I'm trying to get that back up here. Where you're going to look at relationships, which is through a balanced reaction, and you're going to see, okay, if I need this much product, mathematically, this is how much reactant I need to start with. Or maybe, like I said before, here's how much reactant I'm starting with. How much product am I going to make in the end? And everything goes back to these, what's called a mole ratio. And your mole ratio is kind of the heart of any of these dimensional analysis problems. So when we're doing these stoichiometry problems, they're always going to be set up like the dimensional analysis problems. That's why I drove it home last unit. You have to use dimensional analysis. You lost points every time you were just multiplying or just dividing or whatever else, because we really have to figure out how do you take one unit and turn it into another one, and then take that unit and turn it into another one, because we're going to keep expanding on these stoichiometry problems. This is something that usually in a college level course, this would be day 2 basically. Everything that we've done so far would all be kind of wrapped up into the first chemistry class that you would have in college. Stoic is kind of the basis of AP Chem, which this is pre-AP Chem, which means that you are scheduled to go into AP Chem down the road. And you have to know these in and out all throughout that course. So when we're doing our dimensional analysis problems, the heart of every stoic problem is what's called a mole ratio. And your mole ratio, every single time, is taking one part of the equation and going to a different part of the equation. So you will always take one of your reactants or one of your products, and you're going to see how it relates to a different component of your chemical reactions. So when you're finding your mole ratios, we have to have a balanced reaction. And how we read balanced reactions before is one molecule and another molecule, or one particle, or whatever you're dealing with. And we were dealing with it on the particle level. Now, when we look at mole ratios, when you look at your balanced reaction, you're not going to read it as one molecule or one formula unit or one atom. You're going to look at it in terms of 1 mole or 2 moles. Whatever that number is, the coefficient up front, that number is going to relate to the number of moles that are there. And you're going to pull those and use it as a ratio. So I'm actually going to switch over to my document camera to do this one that's up here on the screen. See if I can do this. There we go. I'm going to make this a little bit bigger because I have more screen. There we go. And in this problem, it says, how do I get a mole ratio? And the answer there is use the balanced reaction. So I gave you an unbalanced reaction, and you're going to see these a lot throughout your Stoic unit, that you're going to have to write out a balanced reaction. Sometimes you have to predict your products. In this case, you don't. This says oxygen reacts with hydrogen to make water. Oxygen is O. The only time you have a number, with your symbol is if it's in Brinkelhoff. Your diatomic elements, oxygen is in Brinkelhoff. It's reacting with hydrogen. Again, we have a single element. That one is in Brinkelhoff as well. It gets a 2, and we are making water, H2O. Now we have to balance this reaction. In order to balance the reaction, remember you put coefficients in front of the symbols. I have two hydrogen and 2 hydrogen. Those are balanced out. I have 2 oxygen. I need 2 oxygen over here, so I put a 2 for my coefficients. That 2 tells me now that I have 2 moles of water. So I have 2 moles of water here, 2 moles of water there. That changes my hydrogens to 4 moles. So now I need 4 moles over here. So when I'm reading this, we have a blank, but that actually means 1. And I'm going to physically write that number 1 for right now, so that way you see what I'm reading. So the way that this reads is 1 mole of oxygen reacts with 2 moles of hydrogen in order to form 2 moles of water. So when I need a mole ratio, it's going to tell you that you have oxygen versus water, or oxygen versus hydrogen, or hydrogen versus water. It'll tell you the 2 that you're dealing with. And when it tells you the 2 that you're dealing with, like let's just say that the problem has to do with oxygen versus water. When we get the mole ratio, it will be 1 mole of oxygen for every 2 moles of water. So that 2 comes from right there, that 1 comes from right there. It's a conversion factor that we're going to use in our dimensional analysis. Now maybe you have a problem that's between hydrogen and water. The way that this would read for your mole ratio is 2 moles of hydrogen for every 2 moles of water. Or another possibility, maybe it's between oxygen and hydrogen. It wants to know the mole ratio there. For every 1 mole of oxygen that you have to have 2 moles of hydrogen, hydrogen, not water, sorry, hydrogen, in order for it to react. So it's a 2-to-1 ratio. Or for every 1 mole of oxygen, you're always going to produce 2 moles of water. So when we get these mole ratios, they're going to tell you what you need to deal with. You have to balance your reaction. And these numbers right here for your mole ratio just comes from that balanced reaction. You just pluck them out and you put them down in your new one. I do have a second example here. In class, we'll do a demonstration with silver 1 nitrate. I'll put pictures in your notes here, but you won't have it, obviously, while I'm doing these problems. Where it says copper reacts with silver 1 nitrate. We need to predict our products. I don't even know what products I'm making at this point. So we're going to take our copper. Copper is a single element. It doesn't get a number unless it is part of Brinkelhoff, which it is not. What's going on here? Okay, there we go. Copper is reacting with silver 1 nitrate. So that means that silver has a +1 charge. Nitrate is NO3 - 1. So you end up with AgNO3, +1 and -1 charge. I'm going to have to balance this out eventually, so I'm going to leave a place to balance it. I need to predict my products. So when we predict our products, I have copper all by itself, and then I have silver 1 nitrate, so AgNO3. For my product, when I go to balance this out, when I go to, reswap and drop, we have silver and nitrate. In this case, copper is not, it doesn't have a charge. We don't know what it is. That's because it's a transition metal. I would have to tell you in this case that we are using copper with a +2 charge. So we're going to cross our partners. So we have copper. It's going to make a compound with nitrate, so Cu NO3, 2. And then, I don't know why I put that there, sorry. I don't have anything for silver to pair up with, so I'm just going to put Ag. It's not a part of Brinkelhoff, so it doesn't get any numbers. I don't care that it's silver 1 at this point, that just means that it's carrying a +1 charge. So now I need to balance my reaction. When I go to balance my reaction, I have 2 nitrates, so I need 2 nitrates over here. That gives me 2 silver, so 2 silver. Everything else now is balanced. In these blanks, I typically don't write it, but now I actually have a 1 that I'm going to use for my mole ratios. The last step, it says determine all the mole ratios that are possible. Now, normally it would tell you, hey, you're dealing with this and this, or this and this, or whatever 2 components. It just wants to know what are all the mole ratios. Typically, you won't have to do that. So this is 1 mole of copper will produce 1 mole of my Cu, NO3, 2. I don't know what I did there, sorry. A different mole ratio for 1 mole of copper, I'll produce 2 moles of silver. So again, this number is the same as here. This number is right there. Now another possibility, looking at my reactants versus my products, for every 2 moles of my Ag NO3, I'm going to produce 1 mole of my Cu NO3, 2. Same thing, for every 2 moles of my Ag NO3, I have 2 moles of silver. Now I have my reactants versus my products. I don't have any other combinations there, but I do have one here where I have 1 mole of copper. And if I have 1 mole of copper, I have to have 2 moles of AgNO3, silver 1 nitrate. Looking at just my products, for my 1 mole of copper 2 nitrate, I have 2 moles of silver. So when you're looking at these, you're looking to see how they relate to one another. Usually you only have to deal with one of these, but in this case it asks for all of them. You will not have a question like this on the test. I was just showing you all the different combinations that were possible. Now in the next video we're going to use these mole ratios where we're going to do a mole to mole problem, and I'll show you where these numbers actually come from, or where the compounds actually come from with a real reaction. So I hope that this helps with your mole ratios. Your next type of problem is going to be mole to mole, where you're going to have moles of one thing and you're going to relate it to moles of another thing. If you guys have any questions, make sure that you ask. That email address is mgable@crosbyisd.org. Have a good day.